Welcome to EDU World Space.
Alright, so to begin, we must identify that the electric field is a negative gradient of the potential and is mathematically shown by this following equation. So the electric field is the derivative of, so dV over dr. So now, given that the potential, so now if we assume that the potential is V, let me use a different color. So if you assume that the potential is V, so in the positions, so if you compute it into Cartesian form, this is the Z. So now if you say that the potential at a given point is this, so A x y minus B x squared plus cy. So here A, B, C are constants. So now we can execute that the x component of the field is, so we can combine these two. We switch back to black, so it's E, the electric field at point X is equal to, once again, it's equal to this, and now we can compute this as D, so the radius is dx, so we can change the r to dx, and now the potential is just this. So let me copy it, move it right here. Yeah, so as I said before, now if you move it there, yeah. So now if we execute this and just derive this with respect to x, we can get that it's equal to negative ay plus 2bx, since when we derive it, just the 2 goes there, and the x becomes of singular power. And since there is no x here, the constant just goes to 0. So now, now to find the y component of the field, so if you did the y component, so at y, now once again we're going to have to derive it, so dy. So if you copy this again, and now we derive it, so we're going to get that. So now if you derive it with respect to y, since there's y to the power 1 here, it just becomes ax minus ax. Don't forget the minus in front of the d here. Minus, and since there is no y constant here, this just turns to 0, and this, there is y to the power 1, so it just becomes coefficient, which is just c. So now if you find the electric potential at c, so d over dc, and as you can already probably tell just by looking at the, sorry, so this dz, hold on, let me write this a little bit better. So this is the c. So as you can probably tell just by looking at the green formula here, there is no z constant, so we can already guess that here, let me just move it first so we can know for sure. Get this whole thing, move it down here. So now since there is no z constant here, this will just equal 0. So the potential at c is equal to 0. And that's the answer to the first part. And now for part B, so for part B, for the electric field to be 0, each component of the electric field must be 0. So that means all these components must be 0. So the potential at EX, potential at EY, and the potential at EZ, which is already equal to 0. So now, so if you assume that, let's start with EY, so the potential at Y. So if you set this equal to 0, so let me start again. EY, remember this has to equal 0 for the electric field to be 0, so each of the components must be 0. So let's start with EY first, since EZ is already 0. So now this negative AX X plus C is equal to 0. So now if you do a little bit of algebra, you can find that X, if you move the C to the other side, sorry, this is equal to 0. So if you move to C to the other side and then divide the whole thing by negative A, we're going to get that it's X is equal to negative C over A. And now if you do, when the X component is 0, so let's set this equal to 0. So now EX, sorry. So we know this also has to equal 0 because this is another component. So now this is equal to negative AY plus 2BX. And we know this has to equal 0. So this implies, so if you do a little bit of arithmetic to solve for Y, we can just move this whole thing to the other side. So it's negative 2BC over A squared. This is if we substitute the X here in, so if you substitute the X from the previous equation into this and solve for Y, we're going to get that Y is equal to negative 2BC over A squared. And remember, these are just the constants. So now, since the potential is independent of Z, for any value of Z, the component of the electric field is 0. That is, EZ is equal to 0. So we don't need to worry about the EZ since it already equals 0. So now V is equal to 0. V is independent and it's not dependent on Z. So EZ is equal to 0 everywhere. And that's about it for this question.